Uh, Hello, my name is Adam Milstein, and I'm going to talk about the Computational Reconfigurable Imaging Spectrometer, or CRISP. And this is in collaboration with my colleagues at MIT Lincoln Laboratory, Ryan Sullenberger, Chuck Wynn, Jerome Lachlan, Corey Smeaton, Phil Chapnick, and Steve Wayman. This is our ACT-17 project. Next chart, please. So just to motivate the work, the problem that we want to address with this work is that traditional remote sensing instruments are expensive, they're large, they've revolutionized the world of weather forecasting and climate measurements, but they tend to have long development cycles, high consequence of failure, and the world is sort of moving towards constellations of small satellites, smaller instruments, more redundancy, and so forth. And so that's what we wanted to address. We wanted to address sort of the expense of the size, weight, and power, see if we can miniaturize, lower costs. Next chart. So our sensing approach is called CRISP, and so this looks a little bit different than a traditional spectrometer. It's a coded spectrometer. And the principle of operation is illustrated with that sort of smiley face scene that you see there. So the scene is dispersed by a prism or some other dispersive element like a grating, and it is re-imaged onto a binary mask. And what you see here in this encoding part of the picture is that each color of the scene lands on a different part of the mask and is thus encoded with a different spatial pattern as it is transmitted through the mask. And then the scene is spectrally recombined by a second prism and imaged onto a focal plane. As we make a series of measurements by flying with platform motion or scanning the sensor, then we have a series of encoded measurements where each color is encoded differently, and we can reconstruct a spectrum at every point, a spectral data cube. And a little more details in the backup charts, but we can show that this type of sensing approach has sensitivity advantages over traditional designs. For example, the multiplex advantage, because like FTIR sensors, we're measuring all of our colors at once. And also from the fact of making an overdetermined measurement. So this is analogous to time-delayed integration, where by making an overdetermined measurement, your measurement count is greater or significantly greater than the number of unknowns. In this case, the number of along-track rows in your imager. So you can average down the noise as well. So in combination, these effects lead to sensitivity advantages that allow us to miniaturize, and we've also shown in some of our published works enable smaller infrared, on-wave infrared instruments that use uncooled thermal detectors. Next chart, please. And another aspect that we wanted to address is the R, the reconfigurability. So we propose that with this kind of sensing approach, different sensing modes are possible. There's the sort of traditional push broom mode that we call drift scan. So that's the sensor is looking downward and the platform is moving. And then you can also do a wide area scan where you're scanning faster, as well as a long dwell mode where you're making sort of multi-angle measurements and semi-staring at a particular spot of interest to build up higher SNR measurements. So the CONOP that you can imagine here is a CubeSat or small-sat constellation where the first satellite identifies something interesting during a wide area search and cues a second satellite to look more closely. So this allows for flexible operation based on interpreting of observations and more intelligent constellation-level observing. Next chart, please. So as part of this ACT program, we've built a breadboard in the long-wave infrared with the parameters shown here. We have a lab one, and we also have on the bottom there a more ruggedized version of the breadboard that has flown on a plane as well. Next chart, please. So these are some example spectra measured in the laboratory, and they show for a spectrometer that works well. We have black body sources, extended sources, as well as narrowband sources, and also transmission to an absorbing gas with a lot of sort of wiggly long-wave infrared features. And in all cases, the prediction and the measurement match up very well. Next chart, please. I'm glad the movie works here. I mentioned earlier that we plan to operate in a sort of wide area scan mode where we're scanning fast. And for certain types of detectors, in particular the type of thermal detectors that we're talking about here, uncooled microbolometers, you want to, one limitation is potentially your frame rate. And one thing about this sensing approach that's very interesting is that the encoding provided by this mask actually the signal is encoded at a temporal rate faster than your readout rate from the imager itself, which allows you to reconstruct, essentially invert the motion blur and reconstruct your spectrum if you make enough measurements. And that's what we're showing. The left-hand side shows the motion blur, the streak that happens if you don't perform this inversion of your motion blur. On the right-hand side, we show recovery of the spatial point spread function by using the encoded signal from this measurement. So this enables us to overcome motion blur and make faster area coverage measurements. Next chart, please. And so, with some internal funding as well, we've been able to do a flight demonstration of CRISP with this breadboard that I've shown here. And if we click, I don't know, hopefully the movies work. If we can click on them, yeah. This the left-hand side there is GoPro measurement, and the right-hand side is the raw frames captured by CRISP. This is on the Lincoln Laboratory Cessna aircraft, which is used for these kinds of flight demonstrations. The measurements made by the system look like, if you just look at them, kind of a panchromatic image with a peculiar fixed pattern on it. Turns out that fixed pattern is the encoding of our signal that enables us to get a spectrum from this measurement. And you could see that, this is far from perfect linear motion. We have a little bit of jitter. We have things kind of shifting columns, and yet we're still able, as we'll show on some subsequent charts, to reconstruct spectra by accounting for all of this with motion compensation. Next chart. So here's an example of a coastal crossing, and there's you could see a spectra for sand versus a spectrum for water, and so and in addition you see textbook or sort of literature spectrum as well, and these are sort of emissivity spectra, and so the emissivity spectrum for water looks close to black body, whereas you see the different looking emissivity spectrum for land. So these spectra agree with predictions for sand and water, and this is suggestive of temperature emissivity separation, which is an important product for thermal infrared in sustainable land imaging. Next chart, please. This chart shows a more recent flight measurement where we did a controlled release of sulfur hexafluoride, a trace gas that has a known long-wave infrared peak signature. And you could see on the plot on the right-hand side that this peak was actually detected. We detected a trace gas release as kind of a proof of concept. And the details are in the paper cited at the bottom there. Next chart, please. So, in summary, we've validated some key model predictions for CRISP in the lab under this ACT effort. And with some internal funding as well, we've demonstrated the spectral imaging in flight. Our current emphasis is on developing scan and spectral resolution modes, this reconfigurability, and also identifying the performance limits. We're currently proposing a brass board instrument demo that would aim to meet SLI, thermal IR requirements. and looking at other applications such as SVG and planetary boundary layer, some sounding applications as well that we can be happy to speak to with a little more time. Thank you so much.